Today we're going to talk about two different processes associated with gases, one of which is called diffusion, which should be familiar, and another one called effusion, which is something that is slightly different. So, just a refresher, on the first day of the unit for gases I did a bunch of demos where we looked at how air pressure can affect different things. One demo we didn't get to was where I took my spray of Glade and I sprayed it throughout the room. And if you remember from CP Chem, if I stand in one corner of the room, let's say we're looking at the top of a room, and I'm standing over here, it's going to take a very long time for molecules from the spray that get sprayed out to travel all the way across the room. To go to the other corner, it takes about 2 minutes or so. Now that seems kind of contradictory because we know that gas molecules, according to kinetic molecular theory, they move in straight lines, they move randomly, they have no brain, they collide with each other, and they move extremely fast, on the orders of hundreds of miles per hour. So what explains this process? Why does it take 2 minutes for a molecule from here to go 30 feet if it's traveling hundreds of miles an hour? Well, there's tons of other gas molecules in the room moving around. So we know that as this molecule moves, boom, it's going to collide and bounce and hit all the other molecules in the room so that eventually, over time, it's going to spread all the way throughout the room. The spreading of a gas is called diffusion. Diffusion is the spreading of a gas through a space. So think of like Mr. Shar spraying an air freshener in a room. Or, as you can see in this diagram, we have it very clear here that we have on this side of, whoa, goodness. On this side of the room, we have a gas, and there's this partition, this wall in between. Once we remove the wall, we get rid of the partition, those molecules now have more space to spread about. They're going to move, they're going to be fast, they're going to collide. Eventually, over time, they will diffuse throughout the whole room, and they'll occupy the entire space of the room. That is diffusion. That should sound pretty familiar to us. The new concept that we need to cover is effusion. So how is effusion different from diffusion? Well, effusion is the spreading of a gas through a hole. So before we were talking about spreading throughout an entire room. Now we're talking about a controlled leak, the spreading of a gas through a controlled area. So as you can see in this diagram here, we have the same gas as before. We have the same partition, except there's this little hole in the middle. So now since there's that hole, these molecules, let's say this molecule is moving around, boom, it's bouncing, boom, moving very fast, colliding, hopefully behaving ideally. Maybe it ends up in a direction off a bounce where it goes towards that hole, and then it spreads throughout the space on the other side. And then maybe a second molecule does the same thing a little bit later, and it spreads through. And then maybe a third molecule a little bit later does the same thing, boom, spreads through. What we can see is this is a much more limited and controlled spreading since it's going through this hole. And what we're going to see is the rate or the speed at which this happens is dependent on a property of the molecule. And this is something called Graham's law of effusion. Graham's law of effusion. What it allows us to predict is the rates or the speed at which molecules will effuse depending on one of their personal properties. And what is that? Well, if we want to look at the ratio of two gases, so let's say we have, gas A and gas B. We'll just call them gas A will be 1 and gas B will be 2. If we want to look at the rate or the speed, which I'm going to label as R, the relationship between those speeds is dependent only on one thing, on the molar masses of those two molecules. So just to be clear, it doesn't matter what we call gas number 1 and gas number 2. We could write this also as R1 over R2 is equal to the square root of M2 over M1. Reminder, as I said before, capital M, this means the molar mass, which has units of grams per mole. But what you can see in either case is the numbers are on opposite sides, either in the numerator on one side of the equation and the denominator on the other side. So what that represents is that there's an indirect relationship between molar mass and rate of effusion, or speed. Basically, heavier molecules, if molar mass is bigger, the rate that they effuse, or the speed that they effuse, is slower. Or another way of saying that is lighter molecules effuse at a faster rate. There's an indirect relationship between the two. So we need to know how to apply that knowledge into both quantitative and qualitative problems. So let's do a couple together here first. Example 1. Calculate the rate of effusion of NO2 compared to SO2 at the same temperature and pressure. So let's think we're working backwards. We're trying to figure out rate of effusion, okay? So my goal is rate of effusion. Well, what do I know about effusion? What's the relationship to get to rate of effusion? Well, we just talked about it. There's a relationship where the rate of gas 1 divided by the rate of gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. So let's see, do I know any of this information? Well, nothing's explicitly written in the problem, but I am given SO2 and I am given NO2. I can figure out the molar masses of those. So I check the periodic table. For NO2, the molar mass is 46 grams per mole. And for SO2, the molar mass is 64 grams per mole. Now I gotta plug some numbers in. And you might be thinking, wait, Mr. Shar, how do I figure out which is gas 2 and which is gas 1? It doesn't matter. It doesn't matter what you call which one. As long as you're aware of, if you choose, let's say we want NO2 to be gas 1, we gotta make sure that we plug in the molar mass of 46 down below. So let's go ahead and do that. We'll call NO2 gas 1, so therefore SO2 is gas 2. So therefore we have this relationship where R of, I'm not going to write 1 anymore, I'm going to write rate of my gas 1, which is NO2, divided by the rate of SO2, is equal to the square root of 64 divided by 46. So if I do the math there, that gets me 64 divided by 46, and the square root of that is 1.18 is equal to rate of NO2 over rate of SO2. So with a little bit of algebra, I'll just multiply rate of SO2 on both sides. So now I have rate of SO2 times 1.18 equals the rate of NO2. So, what does this tell us? There's a lot of ways we could represent the answer, but basically, whatever the rate of NO2 is, let's say it's, or whatever the rate of SO2 is, let's say it's 1, then the rate of NO2 is going to be 1 times 1.18, which would be 1.18. So we can see that the rate of NO2 is higher than the rate of SO2. Let's check. Does that make sense? Well, yes, because the molar mass of NO2 is lower than the molar mass of SO2. So since it's lighter, we would expect it to effuse faster. Boom shakalaka. Okay? Another way of saying this is that the rate of NO2 is 1.18 times greater than the rate of SO2. Let's do another example. What is the rate of effusion for a gas that has a molar mass twice that of a gas that effuses at a rate of 3.62 moles per minute? Excuse me. Well, again, goal is rate of effusion. So again, how do I work backwards? Well, I know Graham's law says the rate of gas 1 over gas 2 is equal to the square root of the inverse of the molar masses. So let's think about what's given to me. Well, I know that I'm trying to figure out rate. I know that one of the gases has a molar mass that is twice that of another, and that one of the gases has a rate of 3.62 moles per minute. So you might be thinking, wait, this is a rate chart, where do I plug it in? To rate 1 or rate 2? Again, it doesn't matter. But we just got to be careful with what we plug in on the other side. So let's just go ahead and call that 3.62 the rate of the second gas. Okay? So now we got to plug in some molar masses. Well, we're not given any explicit numbers, but we just know that the molar mass is twice that of the other one. So what we can see is the gas that effuses at a rate of 3.62, its molar mass is half of the rate of the gas that we're solving for. So what we would need to plug in here is some numbers for the molar masses. It doesn't matter really what we plug in as long as the ratio between the two is 2. So, for example, if the molar mass of, we say, of gas 2 is 1, if the other gas has a molar mass of twice that, then that molar mass has to be 2. Boom. Done. We set it up. So now, all we got to do is solve for r sub 1. So I'm going to multiply by 3.62 on both sides. So I get R1 is equal to the square root of 1/2. PEMDAS, do that first, times 3.62. If I do the math, I get 2.56. Check my units for effusion in this problem. It's moles per minute. And I should have 3 sig figs. So boom, my final answer. This gas would effuse at a rate of 2.56 moles per minute. Again, check yourself. Does that make sense? Well, the rate here is less than the rate here, 3.62. And its mass is twice as big. Aha! That makes sense. Faster gas moves slower than, a heavier gas moves slower than a lighter gas. So, we need to know how to apply the Graham's law of effusion to problems quantitatively and qualitatively. You gotta know the difference between effusion and diffusion, and we'll be good to go with these concepts.